All right, so chapter 17. We're now starting to talk about energy again. Haven't seen energy so much since since Chem 101 really. We're now going to start talking about energy in a little bit of a different way. So if you think about sort of the context of what we've done in Chem 102 and just the framing of the chemistry we've looked at, we started out talking about rates of reactions, right? Kinetics. How fast does a chemical reaction occur? From kinetics, we went on to equilibrium, which was the extent of a reaction, right? Does a reaction proceed really, really far to the products, or does it stay such that it's mostly on the reactant side once equilibrium is reached? So we have the speed of reactions in kinetics, and then in equilibrium, we have the extent to which a reaction completes, right? If we have a very large equilibrium constant, we're mostly making products. If we have a very small equilibrium constant, we're mostly keeping reactants at equilibrium once the reaction has reached its equilibrium state, which we know is a dynamic state, right? The products are reacting to form reactants are forming products at the same time. And so we've spent a lot of time on equilibrium. We've looked at just equilibrium in general, right? We've looked at acid-base equilibrium and how that relates to buffers. We've also looked at solubility equilibria. So we've just looked at equilibria from a number of different standpoints. So the next thing we're going to get to, and we will tie in equilibrium to the stuff that we're doing in this chapter. The next thing we're looking at is spontaneity, entropy, and free energy. Essentially what this chapter is an overview of is if kinetics is the rates of reactions and the equilibrium is the extent of a reaction, well, the free energy is going to tell you whether a reaction is going to occur spontaneously in the forward direction or not, or potentially in the reverse direction for that matter, okay? So that's kind of a framing for what we're looking at in chapter 17, right? Not the extent of a reaction, not the speed of a reaction, but will it actually happen, at least as written, in a spontaneous manner. So the first thing we need to get into is spontaneity. Okay. So 17.1 is about spontaneous processes and entropy. Okay. So to begin with, right, a spontaneous change versus a non-spontaneous change. Now, when we think about a spontaneous or a non-spontaneous change, just as a note, something for you to think about, this is going to be for a reaction or process as written. Okay? In other words, we're thinking about it as reactants, right? React to form products. Even though the reverse reaction can still occur, we're thinking about it in the forward direction, okay? So a spontaneous change is a change that occurs under specified conditions without outside intervention. Basically, we're talking about something is happening under these specified conditions that causes a reaction to occur without any help, okay? So it occurs so spontaneously, okay? So basically, there are a lot of ways that we can look at spontaneous reactions. One of them would be under certain conditions. For example, water at 1 atmosphere. If you have liquid water at 1 atmosphere and it's -5 degrees Celsius, that water is going to spontaneously freeze. It's going to freeze. It's going to become a solid, right? And the reason for that is, well, we're going to explore that a little bit. Part of it's going to be related to the enthalpy change, right? The heat associated with that, but there's going to be a little bit more as well. Now, for a non-spontaneous change, it's that not that a change cannot occur. A non-spontaneous change occurs such that you have to put energy in, and that's kind of that's the big thing on this, right? It's the continuous input of energy, or something else has to happen, right? You're doing something to this reaction to get it to work. You could be just putting in heat. You could be doing work to it. And so one example would be, hey, if you go cook eggs, right, the eggs aren't going to spontaneously cook themselves, which I suppose is a sarcastic thing to say to whoever you're living with that is hoping for you to make breakfast for them. Or you can think about it as You know, if you want to cook eggs, you have to add heat to them. And so where does that heat come from? Well, you can supply heat by, you know, the fire from a stove. Maybe it's an electric stove and you have coils, electrical coils, so you heat it up using those coils. But in any case, you have to supply the energy that causes the proteins in the egg to denature and cook them. And so that's the idea. That egg isn't going to cook on its own, right? We have to heat it up. So with that in mind, the idea of a spontaneous versus non-spontaneous change is related to the reactants and the product. So you'll notice for a spontaneous change, the example where we have water freezing, right? The reverse of water freezing is actually, with a change of conditions, is really easy to go in the reverse. So if you raise the temperature from -5 to 5 degrees, that water is going to be go from the solid to a liquid. Whereas with the eggs, the spontaneous reverse reaction of cooking them, right? And just by cooling them down, you're not going to cause those eggs to go back into the liquidy egg state, right? So just because a reaction is spontaneous or non-spontaneous doesn't mean that it's necessarily very easily reversed, okay? And so that's a key for us. Reversibility is not something we're really extremely interested in at the moment, okay? We're just interested in, does it happen automatically or not? Now you can think about it, if the reverse is hard to come by, that just tells you something about that reaction being either really favored in the forward versus the reverse direction. And again, it's going to depend upon conditions to a very large extent. So when we think about reactions, a reaction under a specific set of conditions will only be spontaneous in one direction. So classical physics, we kind of talk about, when we think about chemistry, a lot of times we talk about this example of a ball rolling downhill, right? That's our sort of classical physics example of something going from a higher potential energy, right, up at the top of the hill up here, to a lower potential energy where the ball is at the bottom of the hill down there. And when we think about this, in chemistry sense, we're thinking, okay, the ball at the bottom of the hill down here, right, is going to be more stable. Okay. And so in a lot of cases, that's going to be how we're going to frame our understanding of this. But in a chemical sense, there's more to it than just that. If we look over to the right, the burning of methane, we know that methane will burn spontaneously. You may need a spark to get it going, but once that methane has that enough energy to go over that activation energy barrier, right? We know that's an exothermic reaction. That is going to continue going until it uses up all of the reactants. Okay, and so that's a spontaneous reaction when you have that fire, but you do have to give it that spark to get it to go in the first place. Essentially, once you get it over that initial activation energy, that reaction is going to go very much spontaneously. Now, a process that you might think about, because the burning of methane in oxygen is a reaction, a process that you might think about, if we go back to think about our gas chemistry, and you have a two flask system that's connected by a stopcock. So in one of those flasks you have nitrogen gas, and the other flask you have some other gas, in this case iodine. And those two are separated by the stopcock. The gases aren't going to flow in either direction. But as soon as you open up that stopcock, what we know about gas particles is they're moving around randomly, right? They have random motions. And if you open up the stopcock and you let the gases go and move from one container to the other, they will spontaneously do that. It may take some time, that depends upon the diffusion of the gases, but eventually you're going to wind up with a system that has two flasks that are mixtures of both nitrogen and iodine, right? So in that sense, a spontaneous process can also occur. So we have reactions that are spontaneous and processes that are spontaneous. So the mixing of gases would be a process, right? We're not talking about a chemical change here. We're just talking about a difference in the mixtures that we're dealing with, okay? So we have these processes or reactions that can occur spontaneously, and we're going to be able to determine, well, what process or reaction will occur spontaneously under certain conditions, and how we're going to measure that going forward. Now, that being said, we're looking at this right now from a very simple standpoint. It's the what is spontaneous or not spontaneous. But we also have talked a little bit about equilibrium, right? If you have a spontaneous process or a non-spontaneous process, generally, so the way we're thinking about it, is looking at the reaction as written. If we have the reverse reaction, for example, the eggs is for making the eggs in our example here, right? Making those eggs from, cracking the egg and putting it in the frying pan and heating it up and denaturing the proteins, that reaction is non-spontaneous. But also the reverse reaction after that's done is not really a spontaneous reaction as well. You'd have to do something to that to change those conditions in a certain sense, because a lot more is going on there in a chemical reaction. Now, what we're going to find though is, remember, if we look at these chemical reactions and processes as being equilibrium based, right? The more spontaneous it is, the more likely it is you are going to have let's say a product favored reaction to some degree. And so we're going to touch on that a little bit later when we start to relate equilibrium in particular to the spontaneity of reactions. But one thing we're not going to relate to spontaneity of reactions is necessarily the speed of a reaction, okay? So spontaneity doesn't necessarily mean that the reaction is going to be a fast reaction. Now, some reactions absolutely are fast, right? Combustion, right? That's a fast reaction, right? And that's a spontaneous reaction. Okay, so just because it's spontaneous, though, doesn't mean it's going to be fast. Because if you think about rusting, right, the process by which iron turns into iron oxide, rusting is a very slow process. It's still spontaneous. The iron is still going to react in the presence of oxygen to form rust, but it's not, so it's still spontaneous, but it's not fast. It's a very slow process. So there's more to the speed of the process or reaction than just whether it's spontaneous or not, okay? Now we're going to study rust a little bit more in the next chapter when we get into electrochemistry. But it's a process we'll see is actually a couple of different reactions that we can look at, and those proceed spontaneously based on the conditions that are available for that substance, that iron substance, to rust. Okay, but again, speed does not, or spontaneity does not imply that it's going to happen quickly. Okay, all right. And so that's sort of an introduction to spontaneity, right? Spontaneous reactions occur without outside input of energy. Non-spontaneous reactions occur with input of energy. And in general, the reversible for reactions, when we're talking about the reversibility, generally assuming that you have a nice easy equilibrium. When I say easy equilibrium, something like water going from solid to liquid, it can easily go from liquid to solid under a change of conditions. So the reverse process can be spontaneous under a different set of conditions for many of the chemical reactions. But something like the eggs, there's more to it than just getting those eggs to I guess, reform in the way that they were, okay? So when we think about spontaneous processes, we have framed processes that we've seen in the past largely based on energies, and in particular, we've dealt with enthalpy changes. Now, back in chapter 6, we did a little bit of hand waving on this, but we talked about enthalpy as being heat, okay? And so we've always kind of dealt with enthalpy changes as the measure of whether something is going from a less stable to a more stable, or from more stable to a less stable state. So that's kind of been our framework so far. Now, I mentioned back in Chem 101, for those of you guys who had me, that, well, there's really more to it than this, but enthalpy is a kind of a good measure for most things about whether something is going from a less stable or more stable state. But if we were really looking at stability of something, if we were really looking at it from a standpoint of, is the product more stable than the reactant? It's not just the enthalpy of the reaction overall. There's a little bit more to a system than just the enthalpy. And remember, we talked about enthalpy, that's the heat generally associated with, say, making and breaking of bonds in a chemical reaction, okay? And so when we think about enthalpy, though, based on what we've done in the past, okay, we think about what we've talked about here, is that when we have a process, that process is generally, well, it's going to tend to go in such a way that the system goes from a higher energy, right, to lower energy, okay? And we can think about that from what we've done in the past with the ball rolling downhill or heat flowing from one object to another. And so if we look at an energy diagram, right, so we have an energy diagram here, well, in this case, an enthalpy diagram, right? So we're talking about enthalpy on the y-axis. And if we say, oh, well, the enthalpy of our reactants is higher than the enthalpy of our products, we get an exothermic reaction, right? And in an exothermic reaction, right, that says that the system, in our case, the reactants, give off energy as they change into the products, right? So the products themselves should be at a lower potential energy, right? So a lower energy than the reactants, right? So more stable for the products. But there's a little bit more to it than just that, okay? So here's the deal, right? If we think about a process, right? Some sort of process or reaction, okay? Our general understanding of whether something is stable, more stable or less stable, is related to the enthalpy change of that reaction. So far, right, we've dealt with it from that standpoint. And so we tend to think about things that are exothermic, right? We would expect them to be more spontaneous, because based on our diagram over here, right, if it's exothermic, it's going from a higher energy to a lower energy. So you would expect it to be more stable. But you would also expect an endothermic process to be the opposite of that, right? Non-spontaneous. And for our intuition, it's not always a bad expectation. However, that's not all there is to it. Now, why would we expect that? Well, we expect it, right, because heat flows from a high to a low energy. However, there are processes that are spontaneous that aren't exothermic. For example, if you think about something like freezing of water, right? That freezing of water is exothermic. Anytime water freezes, that energy has to be given off, right? The heat has to go out of those water molecules. And so as that heat goes away, the water molecules compact in, they form this solid, which is slightly less dense than the liquid, as we know. But it's freezing, whatever the conditions, if something is freezing, it must be an exothermic process. However, freezing is not spontaneous at temperatures above 0 degrees. So there's some measure of the system itself and the parameters of that system, right? The conditions for that particular process or reaction. So freezing, although it's exothermic, it's not spontaneous at all temperatures, okay? And so that's kind of a key for us. And we're gonna explore that a little bit more, right? This whole idea that is not spontaneous at all temperatures. Okay, and I want to make sure language is clear on this. It is not spontaneous at all temperatures. It is spontaneous at some temperatures, right? And I'm not saying that it's non-spontaneous at all temperatures, which is different, right? Not spontaneous versus non-spontaneous. Non-spontaneous means a very specific thing, right? So it's not spontaneous at all temperatures. It is only spontaneous at some temperatures. Now, an example of something that is endothermic, that is a spontaneous process, is something like the dissolving of ammonium nitrate. So ammonium nitrate, you can see my example here is an ice pack, right? These instant ice packs that you have, right? So basically these instant ice packs, they have like water or maybe ethylene glycol, which has some similarities to water on the inside. Basically, hydrogen bonds well. And so it can form ion dipole interactions. And if you take this pack and you have to crush it first, because on the inside of this container, there's another little packet in there that contains this salt. And ammonium nitrate is a common one that's used for these instant ice packs. Because as ammonium nitrate dissolves, it actually, so if you think about it, right, this chemical reaction would be ammonium nitrate dissolving to form ammonium ion, 4 plus nitrate, aqueous, right, as it dissolves. And that particular reaction has an enthalpy change that is positive. So that's an endothermic reaction. But as soon as that ammonium nitrate hits the water, it's going to dissolve spontaneously. Okay, so that's a spontaneous process that's endothermic. And so the result of that is, well, in order for this reaction to occur, it has to draw heat in from somewhere. It draws heat in from its surroundings, assuming that the temperature is such that it can allow it to do that. But basically, it's pulling this energy in spontaneously from its surroundings, okay? And so it feels colder to us because the temperature, and really you can think about it, it's pulling the energy in from itself, right? So the temperature of the substance of this system goes down as the stuff dissociates, and then it's trying to pull in the energy to get back to equalize the temperature of its surroundings. It's pulling in that energy from you. So it actually is decreasing the temperature because of it's the chemical reaction that's driving forward. Okay. So there's an example of something that's endothermic but is spontaneous. Okay. So what is it that causes the spontaneous nature of a reaction? It's this thing that we've talked about in Chem 101, but never dove deeper into. It's called entropy. Okay. And so entropy is the driving force. This is basically what causes a reaction to be spontaneous in the whole. Okay. So first off, what is entropy? Well, entropy, it's really it's a thermodynamic function. Okay, so think math, right? Thermodynamics. We're not going to dive super deep into the thermodynamics of the calculation of entropy, but we need to know sort of how it comes about. But it is this function. And describes a couple of things. One is the arrangement of the particles, so like based on where their position is. And it can describe the energy of those particles as well. So as we get into this discussion of entropy, we're going to start to think about entropy from the standpoint of position initially, and we're going to keep it as simple as possible. We're going to be really specific with our positional discussion on entropy. Is it here or is it there? Whereas if you say, take a gas, right? A gas has many particles. Those particles can be moving around, but there's a lot of different potential or possible positions for those particles. We're going to keep it really simple in our early discussion of entropy. So you can really start to get a feel for what entropy means. And then we're going to kind of add some thought processes to this to get it to be easy to grasp sort of how complex this can be. Okay. Now you may have heard of entropy as being described as disorder or randomness or messiness. I feel like the high school teacher example of this is your room, right? You have to keep your room clean. You have to put the work in to make sure your room stays clean, right? Otherwise, you have clothes strewn about, and I think, you might have toys or books or whatever you have in your room starts to get messy, right? And so that's sort of an oversimplification of really what entropy is, right? You don't have a room that has a higher entropy just because everything's strewn about. A better way to look at it is really how is the energy of a system dispersed among all of the parts of that system, right? So here I say, or you have in the notes here, that entropy can better be defined as a description of the dispersion of energy, right? The more ways that a state can achieve a certain distribution of energy, spread it out more, the greater the probability there is of finding a system in that state, okay? So we're basically, larger volumes will have higher entropies because you can find the gas particles in more different positions, for example. So it's a dispersion of that energy. Where can that energy possibly be is sort of a way of thinking about the entropy of something, okay? So when we look at entropy, hold on, let's see where I have this. Excuse me a second. I'm missing a slide in here. Okay, so I'm gonna add something to, well, we'll add something to this discussion a little bit when we start to look at spontaneity and entropy, okay? So we're gonna keep this nice, simple example to illustrate the entropy of really simple systems, okay? Now, the way we're gonna do this is we're gonna start out by saying, if we have, again, we're gonna use the gas with 2 flasks and a stopcock as our basis for this discussion. So we're talking about a gas that can be in one of 2 flasks initially, and when you open that gas, the gas can flow into the next chamber. And what happens to the entropy? For us, we're keeping it really simple. We're gonna start with 1 particle. Okay, and our condition, our positional condition, okay, is gonna be the right or the left flask. Okay. Now that's oversimplified, right? The position of the particle can be anywhere in that 3-dimensional volume, but for us and for our initial understanding of this, we're gonna look at that 1 particle either on the in the right flask or in the left flask. Now initially it's confined to 1 flask, okay, to the left side, say. When you open the stopcock, right, that gas particle can flow to the other side, right? So that gas particle, right, if it can be now, after the stopcock is open, you have 1, or before the stopcock is open, there's only 1 possibility. Afterwards, there's 2 possibilities for where that particle can be, okay? So what you've done is you've increased the entropy of that system by increasing the volume, okay? In this case, you've doubled the entropy by doubling the volume, okay? Okay, so if you now make it slightly more complex and you have, instead of 1 particle, 2 particles. Okay, now you have a green particle and a red particle, okay? And again, we're talking about them in the gas phase. Initially, they're confined to the left side. And so how many ways can they be confined to the left side? Well, there's only 1 way that those particles could possibly be in 1 flask. But as soon as you open the stopcock, those particles can flow freely. And now you can find them either still remaining in the first flask, or the green particle, right? In this case, if we're distinguishing between them, the green particle and red particle could both be in the second flask because they could both flow over there. Or you could have the red in the left and the green on the right, or the green in the left and the red on the right. And so as you go from the initial state of both particles being in one side, right, where there's only 1 way that can happen, as you open the stopcock and you double the volume, the number of possible ways those particles can be distributed is now multiplied by 4. So you double the volume, the number of, and you have 4 different ways that this can be distributed, okay? So when you had 1 particle, you had 2 different ways. When you have 2 particles, you now have 4 different ways, okay? Now, remember, we're talking only about two possible conditions, left or right here. If we make it again more complex, right, and now say 3 particles. If we have 3 particles, now we have red, green, and blue. Initially, they're all in one side. There's only 1 way that they can all be in the left flask. If you open the flask, now you can have them all 3 flow into the right flask, or maybe the red and the blue one flow into the right flask and the green stays in the left, Or maybe the green and the blue can be in the right flask and the red stays in the left. Or maybe the blue stays in the left and the red and green go to the right. Or the red and green on the left and the blue on the right. Red and blue on the left, green on the right. Or blue and green on the left and red on the right. So now you've gone from, with 3 particles, when you doubled the number of possible conditions, you now have 8 ways that you can distribute those particles in the flasks, okay? And so the idea of entropy is the entropy of a system, when you have more possible conditions, the number of ways that that system can distribute those particles under those conditions is going to increase. So with more conditions, you have more possible ways of distributing them. Also, though, you'll notice when you have more than one possible condition, the number of particles is going to have an impact on the ways that those particles can, or the number of ways that the particles can be distributed, okay? So how does this actually relate to a real gas, right? Because this is really simple, right? We're just talking, you know, right or left or right, right? That's a really simple position, right? However, inside a given flask, those particles can have more conditions, right? Those particles are in 3-dimensional space, right? Which means that we're not limited to just right or left. Now we have particles that can be anywhere over here. For example, if we have a nitrogen gas, you could have nitrogen gas particles anywhere throughout this container that we have over at our right. Right, so now we have almost, you almost look at it as being like an infinite number of new positions. And we can sort of consider those positions all to be confined within the volume of this flask. So those particles can be pretty much anywhere in this flask. And so that starts to add complexity to our description that we're looking at with just the right or the left flask, okay? And so position-wise, we have 3-dimensional space to account for. When it comes to energy, right? Because we said, if we go back up to our discussion of spontaneity or of entropy, we said, okay, well, if entropy is related, or spontaneity is related to entropy, and entropy describes the arrangements of positions and or energies available, well, we now need to think about the energies that are available. Now, the energy is going to be based on, well, largely what we're going to talk about is, at least initially, is just going to be for a process, for something that is moving, the entropy of, say, a gas. Now, energy can be associated with bonds also, but we're going to leave that for a later discussion. So the energy of the particles in a gas are going to be the translational energy. Okay, so that's the energy of moving through space. Okay. And so we can think about it as, well, this nitrogen gas particle in the middle is moving through space, let's say in that direction, but it could be moving in any direction, and these other particles are all moving as well, right, in some way. Okay, and so that's going to be our, I'll shift colors here to try to separate our different descriptions, okay? So our next description is rotational energy. Okay, so when we talk about rotational energy, we're really talking about the bonds vibrating. Excuse me, I'm getting ahead of myself. The bonds, the molecule rotating in space, tumbling, okay? The molecule rotating in space. And so for that, you could think about, okay, how does something rotate? Well, I can think about this molecule as having a number of axes associated with this. Okay, so we've got it's really hard to do this. We've got our, let's call that the z-axis. We've got our x-axis. And say our y-axis. Okay. And so you could think about a molecule rotating. Is it rotating around one axis, maybe two axes? right, or some combination of those three axes, basically this molecule is tumbling in space. That kind of energy is what we call rotational energy. It takes energy to cause something to rotate. Once that thing has that rotational energy, it will continue rotating, assuming it's in a vacuum and not picking up friction, etc. But something that's interesting about these energy states, the translational, rotational, and vibrational energies, the vibrational we'll get to in a second, is that they are all quantized similar to what we talked about with energy levels of orbitals. There are quantization to these energies, how much energy can be absorbed. And I'll talk about the magnitude of these quanta, of the difference, the magnitude of the differences between these energy levels in just a second, okay? The third one to look at is vibrational energy. Okay, so for vibrational energy, we're looking at bonds stretching. Okay, and so in this case, you might have this nitrogen atom here can stretch, and so it's relative to this one. Okay, so but of course it could move in the other direction also, right? So we can think about these molecules as stretching, right? The atoms are moving back and forth, right? They're vibrating. Okay, so they can be moving through space, they can be tumbling, and they can be vibrating all at the same time. Now, that's assuming just the gas it has that energy of movement. There's some other types of energy also. There are energies like electronic transitions. Right, and if for that you can think of the hydrogen atom, right? The electron moving from a higher to a lower energy level, changing energy levels. Suppose I should change my color of my pen if I'm doing this, right? Maybe I'll use a different color and rewrite that in there, make sure it's not getting confused with my vibrational transitions here. Okay. All right, so we also have these electronic transitions. Right, so an electron can move energy levels. And if you think about these as being sort of the, for a given molecule that's intact, that's not reacting, the electronic transition is just, hey, you bump an electron up to a higher energy level. That's going to be a pretty big, okay? So this is going to be actually, of the ones that are listed here, kind of the biggest, okay? So you can sort of think about that as number one of these particular different types of energy. Electronic transitions are large. They deal with a lot of energy. The next would be, so number two would be, so this would be second biggest, right? So this would be number two, would be vibrational energy, the vibrations of these molecules. Now, when I say that those are the second biggest, right? We're talking about the energy of the transitions going from one energy state to another, right? Electronic transitions are very big. Vibrational transitions are are actually considerably smaller, and smaller than that are rotational and translational, right? The translational energy levels, basically, you can have very small differences in speed, very small differences in the rotational energy to go from one quantum of rotational energy to it's almost continuous, but it's not quite, okay? And so when we think about now the complexity of the system, we went from our example here where we had right or left, right? Only two possible conditions to, well, depending upon how much energy there is in a system, that particle can be moving through space, it can be rotating, it can be vibrating, it could have some electronic transitions that are occurring within it, and its position in space. This becomes a much more complex system. So complex as to be something that we won't dive into all of that so much as, but we will take we'll look at it in a little bit of a different way than just the positions, translations, rotations, and vibrations of molecules. This becomes too complex of a thing for us to do calculations on in a class. That being said, I want us to know what those different possible things leads to, okay? So we have all of these possible ways that the energy and position can be distributed within a given system or a given container for a sample of, say, nitrogen gas. And so that leads us to the discussion of entropy and microstates, okay? So microstates are an important way of understanding the entropy of a particular system, okay? So if we think about a gas, right? So all in a system, okay? So if we think about a gas at a certain temperature, right? All of those particles are going to have similar states to them. They're all going to have somewhat similar translational, rotational, vibrational energies and positions. And so each particle is going to be somewhat similar to the others, right? They're particles, they're the same size if you have just one gas, right? And so all these nitrogen molecules, because of their size, their ability to absorb energies is going to be similar, right? They're the same type of molecule. They're going to all be somewhat similar. Well, if you have one particle, right, that has its own state, right? It has some sort of vibrational, rotational, translational energy, maybe electronic energy, position. It's got all of that to it for one particle. Now, we don't tend to talk about gases as one particle, though. We talk about gases as a collection of particles. And the collection of particles, right, where each particle has its own state, right, or it has its own properties, right? We can think about all the particles together that make up the system as having what's called a microstate, okay? And so a system has a microstate that's equal to the sum of all of the states of the particles, okay? And so when you think of a microstate, you can think of it as, well, these particles are in different positions, they all have different energies, and so the energy of that system is dispersed throughout the microstate. It's dispersed throughout the sample of the gas, okay? Now, the number of possible microstates that are available is going to depend on things like how much heat there is in a system, how big is the volume, right? Because the volume is related to the position, right? And so the number of possible microstates for a given system is related to the entropy of that system, just from a qualitative standpoint. You have a bigger volume, there's more possible ways that that energy can be dispersed throughout those particles. If you have more energy, there are going to be more ways that the energy can be dispersed, and that's something we'll talk about also, okay? Now, mathematically speaking, what we've done with our really simple version before is we kept it with a very, very simple setup. We said, okay, there were two possible conditions, right? Those possible conditions were left and right, and we had a number of particles, okay? So if we think about the entropy of a system is based on microstates, right? Well, microstates we're going to abbreviate with this capital W, right? That's the number of microstates. And for our initial system, the number of microstates is related to I, the possible conditions for a particle, raised to the n power, the number of particles, okay? So if we go back up to that slide and think about I, so I was the number of conditions, so I, right, number of conditions, okay, that was equal to 2, right? And the number of particles is the other part of that. Right, that's n. Right, so for the first one, right, if we go up here, right, n equals 1. For the second one, n equals 2. For the third one, n equals 3. So our number of microstates for the first one was 2 to the first power, which is equal to 2. For the second one was 2 to the second power, which of course is equal to 4. And for the third one was 2 to the third power, which is equal to 8. And so we went from 1 microstate where we were just dealing with the closed stopcock and the particle was on one side to 2 microstates. Or we went from 1 microstate where both of the particles were on the left to 4 microstates just by opening up that stopcock. In a third example, we went from 1 microstate where they're all on the same side, all on the left side, to 8 microstates just based on opening up that stopcock for each of these examples, okay? And so the number of particles and the possible set of conditions is what the number of microstates is based on, okay? Now remember, that's just for 2 possible conditions. But again, we were only dealing with those 2 conditions and either 1, 2, or 3 particles. In reality, we know that the number of microstates counts all of the positions, and we can say momenta, right? Really the speeds and the masses of all the particles. But here's the deal, right? You can say the energy, or the number of microstates, is a function of the energy, the volume, and the number of particles, okay? The more energy, the bigger the volume, the more particles you have, the more entropy there will be. And now, these equations here are things that I don't expect you to know. These are the equations that govern the entropy of a system, okay, where G is just a constant. And so for us, you just need to know that as we go to a very complex system, we get way more microstates, okay? And those way more microstates mean that you can distribute that energy in many, many more ways, okay? So if you have a mole of gas, right? Think about just if we just went from, you know, a mole of gas in one side of this container, right? So all in one side, and we were just thinking just positionally, right or left. Well, now you have 2 conditions when you open the stopcock. Now it can be right or left. If you have a mole of gas, that would be 2 raised to the 6.02 times 10 to the 23rd power. So the number of microstates goes to based on the power of the number of particles. And so this is governed by an equation, okay? We know that for a mole of gas, there are on the order of 6.02 times 10 to the 23rd particles. And so when you start to think about and incorporate things like positional and rotational energy, when you have a mole of gas in a given container, you start to think about how many microstates there are, and just by thinking about how many particles there are. And there could be, you know, for a mole of gas, 10 to the, 1 mole, 10 to Avogadro's number of possible microstates, which is just an astronomical figure when you really think about it. And that's why we're not really getting into it more in depth than that. But the number of microstates, like we said, is related to the entropy, and it's related to the entropy via this particular chemical formula, which is the Boltzmann entropy formula. Okay, and more on that in our next slide. So the Boltzmann entropy formula is the entropy is equal to K, that's KB. This is lowercase kb, right? So the lowercase k as opposed to KB from acid-base chemistry, right? If it's a capital B, the B can be the base, the equilibrium constant for the base, right? And so it's S, or the entropy, okay? So S is our entropy. Is going to equal KB times the natural log of W. Now, that KB is what's called the Boltzmann constant, which is just the ideal gas constant divided by Avogadro's number. And so has a value of 1.38 times 10 to the minus 23rd joules per Kelvin. Okay. And so that's based on those number of microstates. Okay, so that's the relationship between now microstates of a system and the entropy. Okay, now to think about why enthalpy and entropy are related, and we're going to see how these go. But we've talked about enthalpy as a thermodynamic function. We did that back in chapter 6, briefly here, but not in the same depth as chapter 6. And now we've just talked in depth about the entropy of a system, okay? Now, when we think about enthalpy and heat, there's really no 0 point for the enthalpy of a system. We've always talked about the entropy. It's just hard to measure something like enthalpy from a 0 point, but we can reference it. So we've always talked about changes in enthalpies, right? A delta H of formation, right? Which was the enthalpy of the system, or excuse me, of a molecule, right? Under standard state conditions, compared to the enthalpy of the elements that made it, right? Under those same set of conditions. And so with enthalpy, we were always looking at a change, a delta H of formation, a delta H of reaction, right? With entropy, you can actually have 0 entropy. 0 entropy is essentially you remove all of the energy. You take all of the energy out of a system. If you take that energy out of a system, there's no energy to disperse. And so at 0 Kelvin, there's no energy in that system. You have what's called a perfect crystal. That's considered a 0 entropy state. Essentially, you've frozen out all vibrations, translations, rotations, and you've reduced the volume to the point where it's only located in one position. And so you basically have, the only thing you have is the particle. No movement, no energy, so therefore no dispersion of energy. So that's how these things kind of differ. So when we talk about entropy, we can have a 0 point for a substance, but that's going to be only at absolute 0. So we're going to see some tables that you've used in the past of enthalpy and entropy and free energy. And the entropy values in those tables are actual values of the entropy as opposed to an enthalpy change, like a delta H of formation, etc. Okay? And so those are things that we're going to deal with and see as we start progressing forward. Okay? All right, so I want us to see sort of how entropy changes to a certain extent. Now, this is where I'm really disappointed that we're not together in class, because I really enjoy what we do in class when we get to this is a simulation, and I'm not sure how to set up a simulation online that would work in the same way. So you're going to have to use your imagination a little bit. And the way we're going to do this is we're going to consider a gas. Okay, so this gas is going to have an arbitrary number of particles. I think there are, if I did this right, there are 26 of us, or so there are 26 students in our class. So I just said we're going to have 26 particles, okay? We're going to give each of those particles one energy initially, okay? Now, one quantum of energy. This quantum of energy, we're just saying there's one type of energy here. We want to keep it simple, so we're saying each particle initially has one energy, okay? Now, of course, we know that based on movement, rotations, vibrations, translations, electronic energy, right, a real particle would have much more energy than this, okay? And we'll come back to that. But for now, we have 26 particles. Each particle has one quantum of energy. Each time particles collide, two things can happen. One, energy can transfer from one particle to another, okay? Or two, no energy can transfer. Now, when we talk about this, we're keeping it simple. Only one quantum can transfer or no energy can transfer, okay? And so we're going to see what happens as we let this gas move, right? As we let these gas particles collide with each other. Now, the reason that no energy might transfer in a collision, it would be an elastic collision. Particles bounce off each other. They keep the same amount of energy afterwards that they had in the beginning, okay? So we're going to simplify this into collision rounds. We're going to look at every particle colliding with one other particle initially, right, in each round, okay? For the first round of collisions, every particle will collide with one other particle. We're going to retally. We're going to go from checking our initial entropy to checking the entropy after one round, okay? In the next round, a particle will collide with a different particle, etc., okay? And so to see this, I'm actually going to take some data from the past, and I'm going to share this as an Excel spreadsheet. Okay. So the first thing we're gonna do, try not to move that part. We're gonna move this over. So initially, round 0, before any collision occurs, okay, what you have here is all particles, as we said, are conditioned. They had 26 particles. They all had one energy, one quantum of energy. How many ways can you distribute that? That's our W. That's our number of microstates, the number of ways you can distribute that. There's only one way that all 26 particles could have one energy, right? Each one has one. That's it. That's the only way you can distribute 26 energy among 26 particles, where they all have one. And so after they collide, you can, we've done this before in simulation in class. Let me see if I can make this a little, make my graph a little bit smaller so you can see it easier. There we go. So after one round of collisions, right, all the particles collided with one other. There are now possible ways of having energy, right? If all the particles initially had one energy and they all collide, two things can happen. They can either transfer energy or not transfer energy. For collisions in which an elastic collision has occurred, no energy is transferred, each particle remains with one energy. That's what we have here. But where there are collisions where energy is transferred, in that first collision, some particles have gained a second energy. So our number of energy you can see here, right? It would be there, but those particles have also taken the energy from others. So some particles would have no energy. And when you do that, you've gone from, with just one collision for each particle, you went from one way of distributing it, where all had one energy, to now you have 7.56 times 10 to the 10th ways of distributing that energy. And so what we can do here is we'll select our data, we'll depict this, right? And so what happens now is, remember we have number of particles and a certain amount of energy here. So now we have a distribution of energy within those particles that remain, right? Some have 9, some have 8, some have 9, some have 1, some have 0 energy, and some have 2 energy. There are 9 with 2 energy, 9 with 0 energy, and 8 with 1 energy. Now, if those particles now collide again, okay, this next set of collisions means that some particles can collide and get 3 energy. Some will collide and be elastic. Some collisions might occur such that particles with 1 energy got 2. Some collisions might have occurred where particles with 2 energy collided and lost 1 to make 1. And some collisions would occur where particles that had 1 energy lost that energy. Now, when you have that second collision, you've now gone from 7.596 times 10 to the 10th possible ways of having it to about 1.4 times 10 to the 12th ways of distributing that. Those are the possible number of ways that you can now distribute that energy. So again, the entropy goes up because you have more ways. So just in 2 collisions, you've gone from 1 to 10 to the 12th ways of distributing, right? And so if we represent that now, we'll select the data for that, you can see what happens to the data. These green dots, or the green triangles, are now for that next round. So you have some with 0, right? More with 0, some with 1, some with 2, some with 3. If we do it again, the next collision, right? In our next collision, now we have 12 with 0 energy, 8 with 1, 2 with 2, 2 with 3, and now we have 2 with 4 energy. And so as we look at that next round of data, we start to see these are the little X's. So you have more with 0 energy, right? The number with, so there's an X right here on the red dot as well. You can see the distribution goes down, and you have 2, 2, and 2. After a 4th collision, you start seeing more energies at higher values, but not necessarily, and also you're starting to increase the number with 0 energy in this case. And so if we depict that, right, we can see these little, this little bluish X here, right? You've got 13, 6, 4, 1, 1, and 1. And if we look at one more collision, right, you can see we distribute that energy in more ways when we add it, when we have that fifth collision occur. Okay, and not only that, you'll notice that with that fifth collision, okay, we're starting to have this distribution, right, where you have a curve in here, right, and you can see that curve, right, is sort of a decay curve, okay? Put that back up there. All right, so you have this decay in here. Now, if this is really simple, this is only having starting with one quantum of energy per particle. And we know that if those particles had more energy, there'd be more ways of dispersing that energy, okay? Now, in this case, it's really simple. You start to get this decay, okay, with that little amount of energy. Now, if we were to have a lot more energy in the system, we would start to add more complexity to it. And some particles we would find have lower energy, some particles have higher energies, and the distribution is going to follow something that's more like what we'll see here in a moment, right? What's going to follow is a distribution that looks much more like what we talked about when we thought about energies and the energies of gas particles with at different temperatures, right? So if we have a higher temperature, or the higher temperature is going to have more possible ways of distributing that energy. It's going to be a broader curve than if we have a lower temperature, which will have more of those particles will have, proportionally more of the particles will have a lower overall kinetic energy to them. And so the distribution, as we get more and more energy, right, higher and higher temperature, for example, which has more kinetic energy, right, we're going to have more possible ways of distributing that energy among the different particles of that system, okay? And so that, for now, that's where we're going to stop, is just this idea of we're dispersing the energy. That energy is dispersed throughout the whole sample, all of the particles within that system that we're talking about. If we have more particles, we can disperse the energy in more ways. If we have a bigger volume, we can disperse the energy in more ways. If we have more energy, we'll have more ways of dispersing energy. And those lead to, that leads to the entropy of a system. Now, what we're going to find as we move forward into this discussion starting on Monday is that the entropy is a very powerful thing when it comes to chemistry. The ability to distribute that energy throughout many different ways is going to lead us to chemistry that can happen spontaneously, and we'll start to do some mathematical derivations of how the energy of a system is related to the entropy and how we can determine spontaneity. And we're going to relate that back to our equilibria in a certain way. And so we'll start to see that on Monday, okay? And so we will stop there for today.